Okay, now coming back for the second half of this, I punched the wrong button a second ago. 133 meters is the minimum length that we would need for that runway. But to be precise and honest, think significant figures, we had only 2 significant figures in all of the numbers that we put into our calculation, so we really can only have 2 significant figures in our final answer. So we'll just round this off to 130 meters. Okay, now let's look at one more example. Imagine a car that's moving at a constant speed for a while, and then it speeds up, and we would like to calculate, and we know how far it goes while it's speeding up, and we'd like to know how much time it took to speed up over that distance. So here are the details. The car is moving at a constant speed for a while, and then we'll say that at this point it starts to speed up. And then we'll say that the speeding up ends right here. We just sort of arbitrarily chosen our time interval to be just the right length so that 3 of those time intervals would be the total amount of time it spent speeding up. And when it starts speeding up, it already has a speed of 20 meters per second, and when it's done speeding up, well, we don't know what the final speed is. But we do know that how far it traveled while it was speeding up. We know that that distance is 50 meters. And we know how the car accelerates. We know it accelerates at 4 meters per second per second. That is, at this moment, it had a speed of 20 meters per second, and 1 second later, it had a speed of 24 meters per second. And then 2 seconds after this time, it had a speed of 28 meters per second, and so forth. So let's again first be clear about what we want for the direction of our coordinate system. Usually we like to have the positive direction in the direction of motion. That's easiest most of the time. So the positive direction is to the right, negative is to the left, and again we want to put the origin of our coordinate system, x equals 0, at the point where the interesting motion begins, at the point where the accelerated motion begins, which will be right here. So this is the point where the interesting motion begins, so it's xi, the location at the initial moment during the accelerating, and we set up our coordinate system, so that's where 0 is. And x final is 50 meters away, so unlike the previous question, now we know x final. So let's think carefully about what we know, what we don't know. Initial location is 0, final location is 50 meters away. Initial velocity is 20 meters per second. Final velocity, 50 meters down the road, we don't know. Acceleration is 4 meters per second, and the length of time it takes the car to get from here to this point 50 meters away while it's accelerating, that's what we're trying to find. That's what we're trying to find. So we need an equation that has delta t in it. and we need an equation in which delta t is the only unknown variable. Well, one equation with delta t in it is this one, v final equals v initial plus acceleration delta t. That's got delta t in it. Delta t is our goal, but we can't use this one because we don't know what v final is. We know v initial, but we don't know v final, so this isn't helpful. The one equation that is helpful, that does have delta t in it, is this equation. Final location equals initial location plus initial velocity delta t plus 1/2 acceleration delta t squared. Delta t is the only unknown in that equation, so let's put in all the other numbers that we do know. X final is 50, x initial is 0. So 50 meters equals 0 plus v initial, that was 20. 20 meters per second times delta t plus 1/2 times acceleration. Acceleration was 4. 1/2 4 meters per second for the acceleration times delta t squared. Okay, now write this just a little bit more compactly. So 50 meters equals 20 meters per second delta t plus 1/2 times 4, that's 2 meters per second delta t squared. And solve for t. The trick here is that, solve for delta t. The trick here is that delta t comes with both a delta t term and a delta t squared term. But way back in your previous algebraic experience, you dealt with these kind of things. It's a quadratic equation, and we have the so-called quadratic formula to allow us to solve quadratic equations. A quadratic equation is any equation that has this kind of form. Some number times some variable squared plus some other number times that variable to the first power plus some third number equals 0. And we could, with just a little bit of messing around, we can rewrite this equation so that it is in the form of a quadratic equation. All we have to do is subtract 50 from both sides of the equation. And then what have we got? We've got now 0 on the right side of the equation, left side, and then this stuff here, 20 meters per second delta t plus 2 meters per second delta t squared minus 50 meters. Let's make it a little simpler by dividing everything by 2. And then flipping these around so that it has exactly the same form as this. Dividing everything by 2, and we start with the variable squared term. That's this. Dividing everything by 2, this just comes out to plain old delta t squared. Or I'll write 1 meter per second times delta t squared. Divide by 2, this is 10 meters per second. Times delta t. Divide by 2, this is minus 25. All equal to 0. Okay, now compare this to this, and we see that A is the number that goes with the variable squared term, so A is just 1 meter per second. And then B is the number that goes with the variable to the first power term. So B is just 10 meters per second. And then C is the number that doesn't get multiplied by the variable. And in this equation, the C term would be minus 25 meters. Now, we use the so-called quadratic formula. And the quadratic formula tells us that anytime we have an equation of this form, then the values of x, there'll be two different values of x that actually solve that equation, that actually make the left-hand side of the equation come out to 0. And they are minus b plus or minus square root of b squared minus 4ac, all divided by 2a. Okay. Well, now all we have to do is put that value of a, that value of b, that value of c into the quadratic formula, and in this case, the variable is delta t. We'll see what kind of delta t we get. So delta t is minus b. B is 10 meters per second, so that's minus 10 meters per second. Meters per second. And then plus or minus b squared. 10 meters per second squared is 100 meters squared second squared, minus 4 times a, which is just 1 meter per second, times c, which is 25 meters, or excuse me, minus 25 meters. And then this is all divided by 2a. There's a, so 2a is 2 meters per second squared. Let's simplify that a little bit. Minus 10 meters per second plus or minus 100 meters squared second squared. And then here's 4 times minus 25. So that's, well, minus 4 times minus 25 is plus 100. Times 1 is still plus 100. Meters times meters divided by second squared, or meters squared second squared, and all divided by 2 meters per second squared. So under the radical sign here, we've got 200 meters squared second squared. So what do our delta t values look like? Delta t is minus 10 meters per second plus or minus square root of 200 meters squared second squared over 2 meters per second squared. And the square root of 200 comes out to about 14.14. So we have minus 10 meters per second plus or minus 14.14 meters per second. I took the square root of these as well, over 2 meters per second per second. So there are two different values, possible values for delta t, depending on whether we take the plus sign here or the minus sign. If we take the positive sign, then we've got minus 10 plus 14.14 or 4.14. Divided by 2 meters per second per second. And 4.14 divided by 2 is 2.07, or about, let's say, 2.1. 2.1 what? Well, the meters here in the numerator is canceled by meters in the denominator, and the 1 over seconds here is canceled by one of the 1 over seconds factors down here. So that one of those goes away, that goes away. So you have here 1 over seconds, inverse of the inverse of seconds, or seconds, just as we're supposed to. So there's our answer. It took 2.1 meters for the car to accelerate those 50 meters when it had started at a speed of 20 meters per second. We know that's our answer because if we chose the minus sign here, then you've got minus 10 minus 14.14, or in other words, 24.1 minus 24.14. Over 2 meters per second per second. That gives us a negative time, and that doesn't make any physical sense. When you use the quadratic equation, you can sometimes you come up with two possible solutions depending on whether you choose the plus or the minus sign. Those will mathematically solve the equation, but it could be that only one of them actually physically makes sense, and that's the 2.1 here. I went into a lot of detail here just because it's good to be reminded at this stage of some algebra that you knew once in the past, because it'll come up several times in the next few days.